Hello and welcome to this design practice 2 module 4. We were talking and discussing about 2-dimensional and 3-dimensional transformations and how computationally you can try to predict the mapping after any operation in space related to objects. And when we are talking about multiple operations done to a single object, obviously there has to be a combined form of equation to compute the final coordinates given the initial coordinate values. And so, in practice a series of transformations may have to be applied in such cases where you need to modify the object through sequential geometric operations, and the technique of combining series of transformations are sort of very useful because it makes computation very fast, and something like this would emerge which highlights the different transformations that are to take place to a vector v in order to give the final value v dash. And so, for a sequence of coordinates which represent a certain geometry in space, if these series of H matrices which are nothing but the homogeneous form of the matrices executing different operations like rotation, scaling, translation, so on and so forth are applied, then quickly you can find out a set of final coordinates given all those transformations in between. This will be more clear when we talk about an example problem where we will actually apply this theory and show you how rotation can be carried out of a 3-dimensional object, a complex 3-dimensional object in space. Let us look at this problem. So, we consider in this particular example problem an object here with respect to x, y, z Cartesian coordinate Cartesian axes, and the various coordinates of the different points of this 3D objects from A to F are mentioned here 353, 753, so on and so forth up to the value of f being 363. So, we want to execute a rotation here, and rotation has to be by 30 degrees and further in the clockwise direction along the y axis. So, the y coordinate does not change, and if we supposing have the rotation around the point D about the y axis, we are talking about this side which is actually parallel to the y axis. So, we want to rotate this in space by 30 degrees and we want to find out what is the final transformed coordinates between A to F which describes this object, so that we can re-represent after rotation the whole object in space. So, this is a very simple operation of a drag and rotation kind of an operation which you normally do on a CAD platform, but what I want to show you here through a series of these geometric transformations is how complex is the computation, the back end computation which keeps on happening, and obviously because of the processor speed you can get immediately the re-representation probably within less than a microsecond probably would be taken for doing all this, so that you can immediately almost view the object being reconstructed. So, in this particular operation, because we have mentioned about rotation carried out along the along a certain plane, this happens to be the x z plane along which the rotation would happen. Also, we must remember that the rotation cannot just happen at this point in space, because the vectors that we talked about while generating the rotation equations were typically with respect to the origin. So, therefore, this set of points being several vectors have to be mapped with respect to the origin in order to see what is the rotation being carried out about the origin. So, our best strategy here which will simplify the process is to translate the object from its existing location back to the origin. This is shown in figure B here, the object comes to the origin, and then you rotate the object around the origin by about the y axis, about the D point, actually about the DE line, because E and D are almost parallel to the is parallel to the y axis. So, rotate the object by 30 degrees in the clockwise direction in the x z plane around the y axis after translating it to the origin. So, D becomes the origin. So, therefore, we need to apply a translation equation to these set of coordinates where we exactly deduct the coordinates by -3, -5 and -5. So, that D becomes 0 0 0 and the remaining become in accordance the new coordinates. and then after performing rotation and using the rotational matrix, we again retranslate it back. For example, from C to D, you can see that object is now rotated, the final coordinates are formulated, and at D you are retranslating it back by 355 this particular value. So, that the position of D does not change, or probably in this case even E does not change, because D and E are parallel to the y axis. And the remaining others change because of such a translation, and it gives you an idea of what is going to be the final coordinates A dash, B dash, C dash, D dash, E dash, F dash of the object. So, this is quite complex. So, you are going back to the origin, rotating at the origin, taking it back into space into the same point, and these three set of transformation equations can be applied by again this concatenation theory, where H 1, H 2, H 3, 3 matrices are multiplied with the initial vector position, which actually represents all the set of all points, which are in this particular figure. So, there are about 6 points which are there. So, we can try to have a matrix with all those 6 points, and then try to have a homogeneous transformation on that with different transformants. One of them is translation into origin. So, that is first transformant. The second one is rotation about the origin, that is the second transformant. Further, this rotation would be along the y axis. So, we represent H y, and then again translating it back. So, that is the third transformant, and so it is actually a series of multiplications being performed to the initial vector containing the initial point. So, we want to actually solve this problem now and try doing the or calculating physically the coordinates given the values A to E which we have already, A to F that we have already as initial values of the figure. So, since we know how to rotate an object about the origin, we need a sequence of the following fundamental transformations. First, we translate, let us call this operation the T1 operation, the object at the reference point D to bring it to the origin. Then we rotate we call this R1 about the x axis, about the y axis, and finally we translate, we call this operation T2, the point D from the origin to its original position. So, the whole transformation concatenated equation can now be written as the V final, that is the final coordinates of V, point V, equals the multiplication of 3 different matrices T2 R1 T1 to the initial coordinate matrix of the geometry that is at hand. So, we want to now gauge what are those different coordinate geometries which are in hand. So, I can say that the V initial in this case can be represented as a matrix comprising of all the different points, the 6 points. So, it is a 6 by 4. So, we call this 3, 5, 3, 1, 7, 5, 3, 1, 7, 5, 5, 1. Let us keep separating these entities through commas, so that there is no confusion. And then we have 3, 5, 5, 1. We have 3, 6, 5, 1, and we have 3, 6, 3, 1. So, let us just shorten it a little bit, just to change the layout a little bit. So, that is how the initial matrix can be written. This can be plugged back into this zone right here, and let us look at the different other transformant matrix which could be used here. So, I will write T1, and so as you know, the T1 transformation is about translating the figure in a manner so that D becomes origin. So, in this event we will have a transformant written as 1 0 0 minus 3 0 1 0 minus 5 0 0 1 minus 5 0 0 0 1. So, this is the first transformant T1. Similarly, we will have the rotational matrix R1, and this can be, because it is a clockwise rotation. So, angles in the clockwise directions are treated generally as negative angles, and of course, the rotation is about y. So, we are talking about Hy here. So, this is cos of minus 30 degrees. Please refer to your notes from earlier modules where I have already mentioned this for an angle theta. 0 sine of minus 30 degrees 0. Similarly, 0 1 0 0 and minus of sine of minus 30 degrees 0 cos of minus 30 degrees 0 0 0 0 1. So, that is how R1 is, and then we have transformation matrix T2 represented as again 1 0 0, and now it is plus 3, because obviously you have to translate the D back from the origin to its initial position. So, plus 5 0 0 1 plus 5 again, and 0 0 0 1. So, these are the 3 different operations, okay, or concatenations that serially have to be applied to V initial, so that you could obtain V final. So, just to notice here that the angle in equation is minus 30 degrees, indicating clockwise rotation. This is the normal sign convention that we are following from trigonometry. So, that is how angles are symbolized. And so, if I wanted to actually now apply the transformation equation V final equals T2 R1 T1 times of V initial, and I computationally calculate, what I am going to get in this particular case is, upon concatenation, you remember that V dash was a series of such transformant matrices which would lead to the calculation of the final coordinates given the initial coordinates. So, we will have in this case V final as, so I am going to now write down the different terms here. So, in one case we will have 3 plus 2 sine of 30 we will have 3 plus 4 cos of 30 plus twice sine of 30 . In a similar manner, we will have 3 plus 4 cosine 30, 3 plus 2 sine 30. Similarly, the second y coordinate would be 5, 5, 5, 5, 6 and 6. You can see the y coordinate does not change really from the initial to the final, because rotation is around y. So, the x has changed quite a bit, and now we will also calculate. So, this is the concatenated form. I am not, for the simplicity sake, I am not doing the whole computation. I understand that, I expect that you will do it, you will put all the rigor for the different multiplication steps between T 1 and V final, R 2 and T 1 V final, and then again T 2 and the whole product which is there. This is actually the whole product that I am representing here. So, then we have 5 minus twice cos of 30 degrees, we have 5 minus twice cos of 30 degree plus 4 sine of 30 degrees, we have 5 plus 4 sine of 30 degrees, we have 5, 5 and 5 minus twice cos of 30 degrees, and similarly we have 1, 1, 1, 1 as a dummy variable, everything coming off. So, if I wanted to compute this and simplify it further, so simplifying further would yield the new coordinates of the rotated form. Vector. So, the V final becomes equal to 4.00, 5.00, 3.27. I am just trying to simplify through computations, okay, whatever has been represented in the earlier step. So, you have 7.46, 5.00, 5.27, again the dummy variable. You have 6.46, 5, 7 and the dummy variable. You have again 3, 5, 5, 1. Note that the position D does not really change, and so does not E. So, the E also is similar, 3, 6, 5, the dummy variable 1, and then finally the point F changes to 4, 6, 3.27, 1.00. So, if from this I extract what are my new positions A dash, B dash, C dash, D dash, E dash and F dash. So, I would be like able to write A dash as 4, 5, 3.27, B dash as 7.46, 5, 5.27, C dash as 6.46, 5, 7, D dash as the same value 355, E dash to be the same value 365, and F dash to be 4, 6, 3.27. So, that is how the coordinates change. These are the final forms of the coordinate given the values a to f as in the question earlier. So, after this rotation, this is how the new coordinates have to be mapped, and based on that it will give you an idea of how the object is going to be like. So, I am going to close this module now, and then in the next module we will do some more modifications or some more studies related to solid modeling, and then how you can actually get into plotting of 3D surfaces. And from there we will go from just regular objects to irregular objects, where we will use some theory and some concepts of fitting into different situations, so that you have different geometries or a family of curves which can roll out. So, we will try to cover up in the next 1 or 2 modules more or less the regular geometries part and the solid modeling part. As of now, I would like to end this module. Thank you very much.